Okay, today we're going to talk about what's called the small gap approximation. Okay, if you recall, we were talking about shear stress. So shear stress is tau, and that's like fluid friction. It acts parallel to a surface, and it's the fluid pulling on the surface. Okay, tau equals mu du dy, where mu is our fluid viscosity and du dy is our strain rate. Another thing to remember is the no slip condition. So at the wall, the fluid velocity has to be the same as the wall velocity. Okay, so for example, we've got a water skier here, and let's say this water ski is moving at a velocity of u. And here is our lake bottom. It's not moving. Okay, so up here, right at the surface of the ski, our velocity here has to be u, right? The same as the ski. Down here at the lake bottom, the bottom's not moving, so the velocity there is 0. Okay, up here, the ski is going to affect the water. It's going to pull on the water. Okay, so that water's going to start moving. But down here, far enough away from the ski, water's probably not going to be moving. Okay, so there's going to be a region down here near the lake bottom where the water velocity is still 0. But eventually we're going to get to the point where the ski is affecting the water below it. Okay, so that's the kind of velocity profile that we would get with something like a water ski. So let's zoom in really closely to just that area. So here's our ski. What this velocity profile is going to look if you zoom in, it's just going to be something like this, right? And what I've done is make this velocity profile linear. Okay, so basically zoom in far enough to almost any curve, and what it's going to look like is going to be linear. Okay, and linear is good because linear is simple. Okay, and so let's take this and assume instead of the lake bottom being way down here, if the lake bottom was way up here right next to it, so we had a small gap, there's not going to be room to have any kind of velocity profile besides linear. Okay, and that is our small gap approximation. So for example, if we have two plates and this bottom plate is moving at a velocity u1 and the top plate is moving faster, velocity u2, well, the no slip condition says that here our velocity has to be u2. Here at the bottom our velocity is u1, which is slower. In between, since this is a small gap compared to the size of the plates, all you can get is a linear profile. Okay, so if you have some kind of bearing or something like that, where you have two plates moving at different speeds, or one might be stationary, and there's a fluid between them, in that case you can probably assume a small gap approximation and therefore a linear velocity profile. Okay, just to look at shear stress a little closer, again, in this case our top plate is moving to the right. Okay, so from the perspective of the plate itself, that means it's like friction. The water is going to pull back on that plate. So if you're thinking, in the other hand, of the perspective of the fluid, the plate is pulling on the fluid in the same direction as the velocity. Usually we're going to look at the perspective of the plate because we want to figure out what kind of force we need on that plate in order to move it. Okay. From the bottom of the plate's perspective here, let's look at that for a second. This top plate is moving faster than the bottom plate. So the water next to this plate is moving faster, faster, faster. So the water is still moving faster right next to this plate than the plate itself. So the water, in the case on the bottom, it's pulling on that plate in the same direction as the flow, and therefore from the fluid's perspective, the shear stress has to be going in the opposite direction. All right, so the plate would be actually pulling backwards on the fluid in that case because the fluid's going faster than it. So the plate's trying to slow it down. All right, so let's, still keeping in mind those two plates, if the velocity profile is linear then, okay, so I said that makes it simple. So let's think about the slope. The slope is du dy, which is part of our tau equals mu du dy equation. It's our strain rate. The slope of a line, if you take the derivative, you're going to get the slope, and the slope is going to be a constant. That makes it easy. Okay. And basically what you can do then is, remember the derivative was a limit as delta y goes to 0. Well, we don't have to take that limit because it's linear, because the slope is not changing. So we can just say it's equal to delta u over delta y over that whole gap. Okay, so over that whole gap, our delta u is u2 minus u1 over h. Okay, and that is not a function of y. Okay, if it's linear and you take the derivative, you're not going to get a y in there anymore. Okay, so if du dy is constant and mu is constant, meaning it's a Newtonian fluid, then tau is also going to be constant. In other words, tau is not going to be changing as you go across that gap. Okay, so tau, which is mu du dy, is just going to be mu times u2 minus u1 over h. And that is going to be tau not only in the middle, but also at each wall. It's going to be the same. Bottom wall, top wall. And the same as what's going on in the middle. Because it's constant across that whole gap. Alright, so that's going to help simplify everything. So whenever you see that you've got like a bearing or something and two plates moving at different speeds with a fluid in between, think small gap approximation and think linear. Okay. And then you can just say, well, that's mu times delta u over h is our shear stress. All right, so let's go one step further and look at the force. Okay, so still for that same example where you have the one plate moving. In this case, let's say that the bottom plate is stationary, so we're going to say u1 equals 0 and u2 equals u, the speed of the top plate. Let's figure out what the force required on the top plate to keep it moving at that speed u. Okay, so if we do a little free body diagram, should always do free body diagrams, we're trying to find that force, and what is counteracting that force is the shear stress down here, but not just the shear stress, because that's force per area, so it's the shear stress times area to give you the total force on that whole wall. Okay, so your force equals tau wall times your area, and that area is wherever that shear is acting. That as long as it's constant, you can do that. If it's acting all over that whole bottom surface, you're going to use that whole bottom surface along here as your area. Okay, so let's find tau at the wall. Well, we just said it's this. It's going to equal u2 minus u1. Oops, forgot the mu. Mu times u2 minus u1 over h. Right? But our u1 is 0. u2 is u, so mu u over h. Very simple. See, I said I made it simpler. All right, so F is just this. That's your tau wall times the area. Okay, so mu is just going to equal u times the area over h. And if that's some kind of rectangle, that area would just be this length times the width out of the page. Okay, so force, pretty straightforward. Just remember force equals tau times the area. Power, if you remember back to physics, power is different for translating objects and rotating objects. So if we're talking about the power of that plate, it's just translating. So translating objects, power is force times velocity. Force times velocity. Well, our velocity here is u. That kind of makes it easy to remember. Just remember power equals Fu, and you got it. For rotating objects, on the other hand, power is a little different. I don't know if you remember this, but it's equal to torque times angular velocity. Torque times angular velocity. Okay, and torque is going to be like a moment. Angular velocity, you're going to need to have that in radians per second, or radians per some time. Okay, so for this example, we've got a translating object, so we get to use FU, haha, P equals FU. And we're talking about U of the plate because we're talking about power that we need to put into that plate. So that's just going to equal our force, mu A UA over H times U, which, just rewriting, mu U squared A over H. Okay, so there's our power. It's a function of U squared. Okay, so a few little notes before we go. The shear in the fluid, again, it's the same the whole way across for the small gap approximation only. Okay, which means the bottom plate's going to have the same shear stress as the top plate. Might be going in a different direction. And this is only valid, again, if H is small relative to the size of your plates. All right, so little question here. What force would be needed to keep the bottom plate stationary? So this was the force on the top plate, mu UA over H. What would it be for the bottom plate? Well, just remember that the same shear is exerted on each plate. All right, so it's going to be the same. F equals mu UA over H in order to keep that bottom plate from moving. All right, stop here and go ahead and do questions 1 and 2 of your quiz.